We're through this, so we can modify it.
Yes.
Good morning. It's great to see you here. Welcome to an invited talk in the Taming the Data talk series. This talk has been made possible by generous support from SAS, Cisco Informatica, and the MC, and also through generous support by ePartners and the NC State Engineering Foundation. This is my great pleasure to introduce Dr. Christos Faloutsos, for whom this is the second invited talk visit at NC State, and he is going to tell us about large graph mining. So to me, this is a great example of how you approach a very important problem in a successful interdisciplinary way. Dr. Faloutsos is a professor at CMU, lots of honors, awards, accolades, and he will show us what he's capable of. So let's welcome Dr. Faloutsos.
Thank you very much, and I would like to thank Rada for all the hospitality and all the and the invitation. So we'll start with introduction motivation. Why should we study big graphs? Then we'll see part one, patterns in graphs, and then cascade analysis. So large graphs, Facebook, we don't need to introduce. Almost everybody is a member of Facebook. There are other social networks, Google+, Twitter, LinkedIn, and so on. For those who care about money, they generate tens of billions of dollars revenue. For those who care about numbers, they have billions of users. But graphs appear not only with humans, but also with many, many other types of nodes. So here is a prey-predator graph. Which species feeds on what species? So if this species become extinct, for example, maybe the whole ecological network will unravel, and we would like to do something about it. Nodes could be autonomous systems like ncsu.edu, cmu.edu. If two autonomous systems are connected, we have an edge. We want to figure out how this graph looks like, which is the most central node, which is the node we should protect best against viruses, and so on. And the list continues. Blogs. My blog points to your blog. This creates a network of blogs. Who is the most influential blog? Who creates memes that everybody else follows, and so on. Computer security, which machine does port scanning, which machine has been compromised and sends messages to everybody else. Recommendation systems, who likes what, right? This is a bipartite graph. We need to know, some of you may remember the Netflix competition, which was $1 million if you can do better recommendation system than Netflix, right? In general, many-to-many, for people with a database background, there are the so-called many-to-many relationships. Any such many-to-many relationship indicates a graph. So people like products, people like movies. This is a man-to-man relationship. This is a bipartite graph. So first, let's see what patterns we should expect to see in graphs and what is the problem. So let's see some patterns and regularities. So are real graphs random? If we plot, this is a plot of the autonomous systems in 1997. If we plot them carelessly, we get the so-called Death Star. This, we cannot see any pattern, right? It looks like a big mess. But real graphs are not random, right? As I'm sure everybody knows, there are the 6 degrees of separation, right? Or for those of us who wasted time on the Kevin Bacon Oracle, this is also 6 degrees of separation in Hollywood, right? And this is something that random graphs would not have a short diameter. We'll see also skewed degree in and out degree distributions on real graphs, and then we'll see additional patterns. Then we'll answer the question why there are no good cuts, and we'll see that the answer is, for both cases, are self-similarity. So let's look at the data first to see what patterns we can see on graphs that seem like the Death Star. This is again the autonomous systems, April 97. If, again, as we said, if we plot it carelessly, we get nothing. If we plot the degree distribution, actually this is the rank degree, then we see a surprising pattern. So the vertical axis is the degree, and the horizontal axis is the rank. So AT&T.com is the autonomous system with the highest degree, 800, and it has rank 1. IBM, not surprising, it's a telecommunication ISP. IBM.com is number 2, rank 2 with 600, and so on and so forth. If we plot it in log-log scales, a line seems to fit well. So this is a power law in logarithmic scales. The slope is 0.8. This even has a name. Distributions like that have appeared before. I'm sure several of you have heard of the ZIF distribution. The ZIF distribution would be something that has slope 1, but here we have the generalized ZIF distribution. And why is this important? The reason this is important is for people who want to write algorithms and analysis of graphs. This has big impact. If the distribution of degrees was Gaussian, everybody has degree 3 plus or minus 1, then the equivalent plot would be qualitatively different than what is reality, right? And okay, so it would be different still. So what, right? What happens is that the skewness of distribution can lead to extremely fast or extremely slow algorithms if we're not careful. So here's an example, and then we'll close the parenthesis. Consider the situation. We want the very innocent-looking query. We want the friends of friends, right? We log in on Facebook. We have 50 friends. How many two-step-away friends we have, right? That's a reasonable query. It is called FOF, friends of friends, right? So this would say if we have two-step-away pairs, the Gaussian distribution will say everybody has 50 friends, so 50 square friends times a billion, it's okay, it's a few gigabytes, it would fit anywhere. Right? Wrong. What is happening is that the highest degree is what matters. If we have a person who has 10 million followers, and we do, right? CNN, President Obama, news feeds, and so on, right? If they have 10 million followers, then all these followers will create 10 million square two-step-away pairs, which, if my calculations are correct, this is roughly a petabyte, which takes half a room like this one to store and cool and everything, right? And this is just for one person, right? For the most common person. So this will kill the algorithm. This is a snapshot of the data center observatory at CMU, and this is a screen, a 13-inch screen, so you can imagine this is half a room. And so the high-level point is that patterns like that, skewed patterns like that, will need new algorithms. They can either help us if we are careful or can kill us if we are not careful, like the friends of friends situation. And we'll call it the Gaussian trap, and we'll see it again. So we saw that the first static pattern is the degree distribution is skewed. The second static pattern, which we'll need later actually, is that the eigenvalues of the adjacency matrix of a graph are also skewed. So this is almost every plot we'll see is in logarithmic scale. So this is logarithm of the rank, and this is the logarithm of the absolute value of the eigenvalue. So the first eigenvalue is 80, the next eigenvalue is 40, the next is 30, and so on and so forth. We see they sort of fit on a line. We'll see later the definition of the eigenvalue. This is the textbook definition, right? We have adjacency matrix A, million by million, right? X is a million-one column vector. Lambda is the first eigenvalue, and X is the vector that didn't change under this matrix multiplication. But we'll see the intuition later, as we said. Let's see what other patterns we can see in real graphs. Let's see about triangles. So the third static pattern is that there are a lot of triangles. Suppose this is us. These are two of our friends. We throw a party. Sooner or later, we introduce our friends to each other. Therefore, there are many more triangles in real graphs than in random graphs. By the way, please feel free to stop me if there are questions, right? So the question is, okay, can we see any pattern? Of course, if somebody has a lot of friends, this person will participate in a lot of triangles, right? So this person has two friends and participates in one triangle. So if you have twice as many friends as me on Facebook, would you have twice the triangles? Probably, right? But actually, no. What is happening is twice the friends is more or less 3 times the triangles. This is real data. Every dot is a person. The horizontal axis is the degree. The vertical axis is the number of triangles this person participates. And we see that an anonymized social network, opinions.com, Who Trusts Whom, and Reuters text documents, they all seem to have a magic exponent of 1.6, which means double the friends, triple the triangles. Now we're getting into details, but this is to illustrate how careful we have to be when we have big data. So how would we estimate the number of triangles? Suppose we sign up all the non-disclosure agreements, or we get a job at Facebook, and we want to compute how many triangles are in 1 billion Facebook members, right? people with database background will say, well, this is easy, 3-line code, right? It's a 3-way join, select, do the appropriate joins, and then we're done, right? But this will die, right? This will give the correct result after a few thousand years, right? Because the biggest degree is a million squared, right? Or 10 million squared, and this won't work. Can't we do something faster? The answer is, comes actually from textbooks in matrix algebra, which say the number of triangles, it's a homework, that it's the sum of the cube of eigenvalues. I didn't know it, but some friends said that this is true. And actually, it's a two-line proof. So now we can, instead of dying the 1 million square, right, we can compute the eigenvalues. And thanks to the property we saw before, the eigenvalues are skewed. So if we get the top 10 eigenvalues cubed, they will be so much bigger than the rest that we get an extremely good approximation with the top 10 eigenvalues. So, and computing eigenvalues is linear on the number of edges, linear on the number of friendships, which will be several billion, but not million squared, not quadrillions. Let's see what happens with real data. So this Brendan Meader and Yukan, back then graduate student at CMU, they collect data from Twitter, 3 billion edges. So the horizontal axis is the degree, the vertical axis is the number of triangles, right? So not surprising. This is 2008. Barack Obama was still a presidential candidate. Not surprising, has a lot of followers and a lot of triangles because the followers are friends with each other. The question is, what happens to the rest? Should we expect a line? This is power laws again, right? Log. Should we expect twice the friends, twice the triangles, or twice the friends, 3 times the triangles, or maybe none of the above, right? Real data are strange. And by the way, we are thankful to Yahoo for letting us use the M45, a huge machine, one of the top 50 supercomputers of the time, to do all these experiments. What do you guess? Slope 1, slope 1.5, no slope. Actually, slope about 1.5. There are a lot of points here, and we would stop the discussion, except that there is a little cloud of points, about a few thousand points here, which are 4 orders of magnitude above the value they should be. So the explanation is that these people probably form cliques, and they all follow each other, right? Further, why would somebody do that? Can you guess? Fraud, right? These guys are adult advertisers, sock puppets, so they're advertising Viagra and things like that. So it's probably the same person logging in 50 times and following himself or herself around to build credibility, right? And this is something that wouldn't show, right? These guys have degree 10,000, 20,000. They're not that suspicious, right? But once we do the triangles with eigenvalues and the M45, then they stand out. Let's see some anti-patterns. So this is background. The blue background means this is introductory material. Given a graph and a user-defined constant k, let's say k equals 2, we want to break a graph into communities. In this graph, we would say, let's break it into 2 groups, right? This is a bridge, and these are 2 nice communities. And the pictorial representation, the adjacency matrix would be something like that. Everybody from the first group knows everybody from the first group. This is the bridge. Somebody from the first group knows some people from one person from the other group, and that's about it. And this is the Montague and the Juliet and Romeo and Juliet, right? The Montagues, they are friends with each other. They hate the Capulets, right? And only Romeo and Juliet are there, right? So there are 2 clear communities. Okay, so we can do the cut. And there are lots of algorithms to do the cut. One of the most successful one is the METIS by George Karipis and Vipin Kumar, who understand is collaborating with Nagiza, right? There are Fiedler vector, the second eigenvector of the Laplacian, and more, right? So what is happening is that for real graphs, they have strange behavior with respect to cuts. So these are 2 papers that give examples in this situation. So let's see how an intuitive graph would behave. This is all background material, right? Suppose we have nodes on a grid, right? In a finite element simulation, we have a 2-dimensional grid. If we do the cut, so the cut size would be, if we have n nodes, the cut size would be square root of n, right? Under some optimal cut. So if we plot the number of edges we have in the graph versus the size of the cut size, and here is the normalized cut size, we see that initially we have square root of n, then we have square root of n of whatever is left, and so on and so forth. So in log-log scales, if we cut and cut and cut, then this plot, the mean cut plot, will be a line with slope minus 0.5. The lower the value, the better the cut, right? If we have a three-dimensional grid, it doesn't show very well here, but this is a three-dimensional grid, right? Then the slope would be 1 over d, minus 1 over d. The details are not important. What is important is that there is a downward slope. If the graph is random, then it corresponds to an infinite dimensional, more or less infinite dimensional graph. So this is 1 over infinite flat. Okay, so what do real graphs look like? Here is a graph publicized by Google back in 2002. This is the Lucent-Rowden graph, publicly available from this website. Clickstream data, which unfortunately we cannot give out, but the first two are public, right? So how would the mean cut plot look like? Should it have a slope of 1, which means one-dimensional, things on a line? Should it have a slope of 1 over 2, which means two-dimensional grid? Flat, which means random? None of the above, actually. What is happening is that for small pieces, the graphs behave like grids of 2 or 3 dimensions. But for large sizes, they have an upward leap, which is very surprising, right? Which means completely counterintuitive, negative dimensionality, which means our grid analogy is completely the wrong way to think about it, right? If they were two-dimensional grids, then they should have good cuts, right? The lower the value, the better. So we see that they don't have good cuts. At least for large sizes, large graphs don't have good cuts. And this is the Lucent-Rowden graph, same behavior. This is the clickstream data, more or less the same behavior. There is a plateau and then a dip and then a backward solution. But this means that our intuition of grids, 2 and 3 dimensional grids and so on, is way off. What is the right intuition is not clear, but the grid intuition is wrong. Maybe why are there no good cuts? We'll see that self-similarity, a few folds later, will give a possible answer. So let's see some more patterns for additional graphs, time-evolving graphs. This joint work with Yuri Leskovich and John Kleinberg when they were both at CMU. So the first temporal pattern is what happens to the diameter. If we have a balloon and this balloon has n molecules, the diameter should be cubic root of the number of molecules, right? So if we put more molecules in a balloon, the diameter should grow cubic root, right? For graphs, according to some theories and some assumptions, the random graph should have a diameter that grows like log n. If we believe the Barabasi model, the preferential attachment model, then the diameter grows as log n. Diameter is the number of steps we need to go from the furthest away node to the furthest away node. So here the diameter is 1, 2, 3 steps, right?
Grows in terms of adding edges or adding vertices?
It grows in terms of natural growth, which means both edges and nodes. So today, Facebook has, 1 billion people, right? Yeah. Next month, it will have 1 billion, right? So these extra people will have also additional edges. So when a real graph grows, with whatever mechanism it grows, what happens to the diameters? That's the question. Yes, I see your point. Yes, good question. Thanks. Right. So what happens is that the derivations are correct, but the assumptions that these derivations are made are wrong. The diameters shrink over time. Here is one of the several data sets. This is the patent citation graph, 3 million, close to 3 million patents, 16 million edges, publicly available from the USPTO, US Patent Office, and computing the diameter from all the patents up to 75, all the patents up to 80, all the patents up to 85, we see the diameter shrinks. Let's see the second temporal pattern, which may help us explain why the diameter shrinks. So, as we're discussing, suppose that this year Facebook has n nodes, n customers, users, and e edges, e friendships between them. And suppose that we know that next year the number of users will double. What can we say about the number of edges? Well, most people will say double the users, double the edges, right? Why not? Because if we have the degree distribution here and we assume the Gaussian distribution, everybody has what, 50 friends on Facebook, okay, maybe 100 friends, depending if we spend a lot of time. So everybody has 100 plus or minus a little bit, right? So next year, how many users will get? It doesn't matter. They should have 100 plus or minus, right? Human behavior doesn't change. That's the assumption, right? And this would lead to double the nodes, double the edges, right? Makes sense. Well, this is wrong. What is happening? In real data, when we double the nodes, the number of edges almost triple, and this is the Gaussian trap. What is really happening is that the degree distribution follows a power law. This is log-log scales as opposed to lin-lin, right? So this was last year, and we had a strange person who had 10 million friends, right? And next year we have a line will grow, right? So the average will slightly grow, but the average is meaningless, right? Most people have one friend, and there are some people with 10 million friends, so the average is 566. Who cares, right? What difference does it make? But here, with more people, there is bigger chances that somebody will have, what did we say here, 10 million? Somebody will have 20 million friends. The longer we wait, the more strange people will see, right? And this explains why we have, this can explain why we have the densification. Double the nodes, triple the edges. This is real data. Again, the patent office, 75, so many nodes, so many edges, 76, so many nodes, so many edges. We see that some invisible hand keeps this graph in a slope of 1.6. Slope of 1, if the graph was a tree or a chain, the slope would be 1, as many edges as nodes. If the graph was a full click, everybody cites everybody else, which is unrealistic, but let's do this thought experiment, right? The slope would be 2. So we are reality somewhere in between the two extremes. Not a chain, not a full click, somewhere in between, but surprisingly along a line. Are there other patterns? Yes, this is from a paper with Lemana Koglu. There are about 10 or 11 patterns. We saw already 5 of them. We won't spend time to the remaining 6 or 7. But the bottom line is that real graphs create patterns that are surprising. This is a book chapter in Charu's book, Charu Agrawal's book. This is also a monograph with Deepak Chakrabarty with even more patterns. But this is, again, the take-home message. There are a lot of surprises when we have real data, a lot of non-Gaussianities, a lot of skew distributions. So why are there so many power laws? Yes, please.
So all the patterns which you mentioned so far, are they explainable using the power law distribution or not?
The question is...
the patterns which you saw so far, we cannot explain them by a Gaussian distribution, but can we explain all of them using the power law distribution?
Correct. So several patterns we have seen so far, they are explained, the power law distribution fits better than the Gaussian. And we can argue whether a power law is better or a log logistic is better or log normal is better, all of them.
I'm more interested in the exceptions, which cannot be explained by power law.
The exceptions, very good question. So there are exceptions. Road networks are usually, they don't have power laws because you have at most 4 intersections, okay, 8 if the civil engineer was not very good, right, and had, right? But that's about it. You cannot have 50 intersections in a road, right? So the degree is at most 8. So these are exceptions. When there is a hardware limit that you cannot have degree higher than 8 or whatever, right? So, and the diameter is not really a power law, right? The diameter shrinks, so the axes were linear, right? Good question, thanks. Anything else? Because we're getting into deep waters. So, so 2 questions. Why are there so many power laws, and how come there are no good cuts, right? We saw that Montagues and Capulets would be easily separated. Why not real networks? And one possible answer, right, is that maybe this is due to self-similarity. So we'll have a quick introduction, a 10, 20-second introduction to fractals and self-similarity. Instead of giving the definition, let's give an example. So one of the most famous fractals is the Sierpinski triangle, which says all fractals are recursive. So let's start with a triangle, find the middles of the edges, pull out that triangle, continue recursively, do that infinite times. Needs imagination, but we can do it, right? So this is a finite sample of the infinite Sierpinski triangle, and in this way we have holes within holes within holes, right? Opening parenthesis within a parenthesis, what is the dimensionality of this plot? This is tricky, right? It's not one-dimensional because something that is one-dimensional should have finite boundary, right? Here the boundary, every time we drill a hole, the boundary grows by 4/3. 4/3 to infinity is infinite. So this thing has infinite boundary. On the other hand, it's less than two-dimensional, right? Because every time we drill a hole, the area decreases by 3/4, right? 3/4 to infinity is 0. So we have a monster who has infinite periphery and 0 area. So what is the dimensionality of this monster? 2 foils down the road, the answer. So let's see why fractal. The argument is that self-similarity leads to clouds of points that have no characteristic scale, and this leads to power laws. Why we have no characteristic scale and why we have power laws? Suppose here is an example of a power law. Suppose we focus our attention to the 0, 0 point, the black point at the origin. If we double the radius from blue to red, double the radius, the number of neighbors grows and becomes triple, right? Double the radius, triple the neighbors. If we do it carefully, eventually the mathematics say that the number of neighbors for this point grows, is a constant and depends on the radius to log 3 over log 2. Trust me, this is the correct mathematics, right? And this is no characteristic scale, because if we go from the green radius to the blue radius, we have exactly the same situation. So if I show you, if I pull out a little triangle of these Sierpinski triangles, magnify it, you cannot tell whether this was 1/3 replica, 1/9 replica, 1/27 replica, right? They're all self-similar, right? So there's no characteristic scale. And we won't go through the proofs, but this is the case. When we have no characteristic scales, we expect to see power laws. And this reminds us of the real data we saw before. We double the friends, we triple the edges, right? Double the number of patents, we triple the number of citations to each other, right? People will say, wait a minute, this is strange, I don't believe this. Actually, this nicely includes uniform data sets, right? Suppose we have a cloud of points uniformly distributed in the unit square. We do the same thought experiment for this point. How many neighbors you have? Double the radius. As we double the radius, the number of neighbors quadruples. So it grows with exponent 2. And this makes a lot of sense, right? It's a uniform set. And now notice we are answering the dimensionality question. What's the dimensionality of the Sierpinski triangle? The dimensionality is exactly the exponent of this neighbor relationship, right? So here, this is a 2-dimensional data set. The exponent is 2. This is a 1.5-dimensional data set, log 3 over log 2. And this makes sense. It's between the 2-dimensional, which would have area, and the 1-dimensional, which would have finite length, right? So, almost ready to close the parenthesis. The take-home message is that whenever we have self-similarity, we should expect to see power laws, and probably the other way around. Close parenthesis. So let's see what happens, how self-similarity can help. So the problem here now is, can we create graphs that will look realistic? Could we write code which will press a button and will generate a graph with n1 nodes, 1,000 nodes, and then 2,000 nodes, and then 3,000, 10,000, right, and so on. So we would like this graph to be realistic. There's no definition of realistic. Realistic means we set up a few checkpoints like static pattern 1, power law degree distribution, power law eigenvalue, small diameter, right? If our generator passes these 5 patterns, we say this generator passes these 5 patterns and is more realistic than generators that don't, right? Why would we want to do a synthetic graph since we have huge graphs available on the web? Privacy reasons. Sometimes, yes, Facebook has huge graphs, but they won't give it to us, right? So sometimes we want to stress test our graph algorithms on realistic looking data, or ask what if scenarios. What if Facebook grows to have up to 1 trillion, well, it won't be 1 trillion, 5 billion nodes. What will happen in that case, right? So this is a list of patterns we would like our generator to have. And backtrack, as you may have noticed, almost all of them are power laws, right, except for the shrinking diameter, which was mentioned before, right? And we said that self-similarity and recursion gives power laws without even trying. And that's the whole idea behind this Kronecker graph generator idea. So let's create graphs using recursion. Let's start, pick your favorite shape, let's say a chain. Yes?
Can we go back to this?
Of course.
So among all the conditions, S1, S2, and T2, T1, are they all independent of each other?
Very good question. We don't know. so the question was, are these 5 conditions independent of each other? We don't know. We had discussions with Guy Bleloch. Maybe there are some dependencies between them. We don't know. But at this point of time, we are happy if a generator matches all 5 of them. We're very happy, right? And the point is that exactly that self-similarity will help us generate all these properties without even trying. So let's see how we would generate a graph recursively. It's not as easy as it looks. So let's start with an easy graph. Let's say a chain. Could be a star, could be anything you want, but let's say with a chain because the results are the same. A chain would have the adjacency matrix of everything is connected to everybody else except node number 1 connected to node number 3. And for subtle reasons, let's assume self-loops, right? So how would we create a recursive generator? More or less like the Sierpinski triangle. Take a little chain, a 3 chain, and squeeze it into the first node. Right? Take a little chain, squeeze it into the second node, into the third node. And we would stop there, except that the question is how would we connect these 3 little chains? If we connect them just by the center point, it won't work. Why not? We don't have enough edges, and the diameter grew. The diameter here is 2. The diameter here is 1, 2, 3, 4. So with 1 iteration, we kill the diameter. With 2 iterations, it would be a disaster, right? So we are almost there. What is the right way to connect graphs? And actually, there were papers who said, let's create graphs like that. They will have power law degree distributions, but they won't have the correct way to do graphs is through the so-called Kronecker matrix multiplication. I didn't know about it, but it's textbook material in matrix algebra. So the idea is we want a 9 by 9 adjacency matrix, 9 nodes, right? And the idea is that we can take the original G1 matrix and every cell of the matrix will be replaced by a little copy of G1, right? So this is called exactly Kronecker matrix multiplication. I know it's complicated, but if we unravel this adjacency matrix, which is 9 by 9, it doesn't show, but it's actually 9 by 9, right? Then this is the connectivity we get. And this has the 2-step away distribution, right? Everything is 2 step away from everybody else. Diameter is 2. It's not shrinking, but at least it's constant. It's not growing. And if we do 4 iterations of that, we get something that looks like our doilies that our grandmothers used to do. And this makes sense. There are communities within communities. There are some, we can probably break it into 3 pieces. These 3 pieces are not like blocks. They are breaking into 3 pieces themselves, and those break into 3 more pieces, and so on and so forth. So if this looks like the Sierpinski triangle, this is the goal all along. We want it to look like the Sierpinski triangle. We wanted to have communities within communities, holes within holes. And now it turns out that we had these checkpoints, the 5 checkpoints. It turns out that for the three of the checkpoints, we don't even need to prove anything. Kronecker matrix multiplication has been studied a lot, and it turns out that the degree distribution is multinomial, which behaves like the tail behaves like a power law. The eigenvalue distribution is multinomial. The page rank is multinomial. Everything is very skewed. The only thing that was new is the diameter is constant. It took half a page of proof, but we can also prove that the diameter is constant in this case. So this self-similarity led to passing all the 5 checkpoints, and this is the first generator for which we can prove all these properties. All the other generators can prove at most 1, right? The Barabasi, the groundbreaking Barabasi algorithm of preferential attachment proves the degree distribution, but that's about it. Nothing about diameters, nothing about eigenvalues. And actually, tooting my own horn, this is this idea, also called ARMAT, is the basis of the Graph 500 benchmark, where all the major supercomputing groups compete on. They generate graphs of million, billion, trillion nodes, and then they run their algorithms and wall clock them to see whose machine is faster. Let's see why there are no good cuts now. The second question, right? We answered the first question, why so many power laws? Because maybe there's some sort of self-similarity in how nature creates graphs. So Why no good cuts? Again, the answer may be self-similarity. One possible answer may be self-similarity. We have communities within communities, and therefore there is no real natural place to cut, right? So remember, this is the doily. We can claim that these are communities, but these communities they have smaller communities, right? When we say communities, we expect a block diagonal matrix, right? All these people know each other, all these people know each other, and so on. That's not the case. All these people sort of know each other, except that these guys hate the first group, hates the third group, and so on, right? So the question now is how many communities we would like to see here. Would we like to see 3 communities, or 9, or 27? So what is going on? So if we have the best community detection algorithm, what as humans would dictate the number of communities to be? And the answer is, it seems to be one community, but it's not a block diagonal community we would like all along. So here is the analogy, right? We want to find communities in a real graph, which we believe which we conjecture is modeled well by a Kronecker graph. So what we want to shoehorn is to fit a block diagonal matrix, right, the Montagues and the Capulets, on this graph, which doesn't match, right? The analogy, the even easier analogy would be how many clusters, right? We are all familiar with k-means algorithms and so on. We have the Sierpinski triangle. How many clusters, if we ask for 3 clusters, what would these clusters be? Probably the red, the blue, and the green, but we are deceiving ourselves, right? Because if we believe that there is a cluster here, this means that there should be a lot of points here, which is exactly empty, right? And this corresponds, an even easier paradigm is to think of, let's say, 2-dimensional points along a line, so number of songs that our marketing department is selling, and this is the age of the customers, right? Suppose that data show that this is what is happening. Young people buy a lot of songs. Old people like me cannot hear well and they don't buy anything, right? So the marketing department, what they will do, they will never fit a line. They will do market segmentation, which will mean they will fit piecewise part and say, from 10 to 20, you are young and you buy a lot of songs. From 20 to 30, you are middle-aged and you buy less songs, and so on and so forth, right? So what is happening is we are asking the wrong question. We are asking piecewise flat parts when a line should fit well. We are asking for Gaussian clusters when there are not any. We are asking for communities like block diagonal structure when there isn't any. So this is the summary of part 1. Yes, please.
So when you say good cuts, how are you measuring
very good question. So the question is, how do we measure the goodness of a cut? Is how many edges we have within the community versus how many edges are going outside the community. So this is a beautiful cut. If Romeo and Juliet were not there, it would be a perfect cut, completely disconnected.
That's a perimetric number.
Sorry?
That's a perimetric number.
Or there is the conductance, I think, the official name. So there's no perfect answer to your question. That's another very good question, right? But the idea is that a community is good if it has a lot of edges between its members and few edges outside, right? So, yeah. Any other question? Yeah.
I hope I didn't miss it. Did you explain the lip in those earlier graphs?
It does not explain the lip. Very good question. Yeah. So in this case, is actually the cuts will be flat. Yeah. Excellent point. Thanks. Other questions? Okay. So continue. So we saw that real graphs have a lot of patterns that we didn't expect, like the shrinking diameter, a lot of power laws. We should be aware of the Gaussian trap. We should not, since we have 50 friends, we should not assume that everybody else has 50 friends plus or minus. No, the majority has one friend and forgot the password, right, like me, and for Facebook, and there are some strange people who have 10,000 friends, 10 million friends, and they're no good cuts. So, yes, we have time to discuss about the second part, cascades and immunization. So, why would we care about cascades and properties moving over a graph? Because there are many applications, right? Information diffusion, somebody says on Twitter a piece of news, and if it's an interesting piece of news, it propagates very fast, right? Viral marketing, somebody shows a new product, this watch, and people say, oh, this is nice, let me buy the same watch, right? So word of mouth campaign. epidemiology, somebody is sick, this person is sneezing, and everybody else around, with high probability, the neighbors get sick, and so on and so forth, right? So we want to figure out how these how viruses and memes and ideas propagate over network, and how to stop, if it's a virus, how to what would be good immunization. So the problem is the so-called there are many versions of the problem. Let's focus on the fractal immunization, which was actually suggested by a medical doctor, Theodore, goes by Jack Iwashima, from University of Michigan, and colleagues also from Michigan and CMU. So the problem is the following. This is real data, 3,000 hospitals. Every gray dot is a hospital in the United States. Every edge, like, I'm not sure if this is visible. Yeah, some of these edges are visible. These edges means that this hospital sends patients to that hospital. If this hospital runs out of beds, then it overflows to that hospital, right? And the question is that when patients are getting transferred, they carry viruses with them, so we need the receiving hospital should have resources to immunize, to clean the rooms, to make sure that they are staying in an isolated place, and so on. So, given, let's simplify it for pictorial reasons, let's say that these are K bottles of disinfectant. We have K bottles of disinfectant, 3,000 hospitals, we know who goes where, which patients go where, right? Which hospital should we give how many bottles, right? And jumping ahead a few foils, if we follow the current approach, which says every hospital gets the same number of bottles no matter what, completely fair and democratic and politically correct, right? After 6 months, all these hospitals are infected. If we use our algorithm, then only these hospitals are infected. Miami, I guess, for some reason gets infected, then the Michigan and so on, but nobody else. So, here's the problem definition. As we said before, this hospital overflows, sends a patient, the patient carries bacteria, and the government or the central administration has bottles of disinfectants. If the administration decides to give 1 bottle of disinfectant to this hospital, this means that the probability of this hospital to get infected decreases. It does not go away, it's not perfect immunization, it just decreases. So the question is, how to distribute bottles left and right so that we make the edges as weak as possible and to slow down the propagation of the disease as much as possible. How would we do that? The way and how exactly to define the problem? Okay, let's decide on 365 days. Let's figure out whoever has the fewest hospitals infected after 365 days has the best policy. Okay, so how would we solve that? If we have a lot of CPU power, we could distribute the resources. In this example, let's only these 2 bottles in these 2 hospitals. Let's infect a few nodes. We're doing simulation. Let's infect a few nodes, these 2 nodes. Let's simulate the evolution. We know who goes where, right? And after 365 days, we see how many gets infected. Okay, obviously that was not a good choice. So let's tweak our choice and move this bottle to somewhere else and repeat and do it again and again and again, right? This makes sense. This is what our colleagues were doing, right? This takes more than a week because simulations are expensive even on fast and multi-core machines. The algorithm we propose, which is use analytics, is 14 seconds on a laptop, not even a desktop, right? A stock laptop. Lower is better here, right? So here are the plot. This is time, 365 days. This is number of infected people. Lower is better. This is what happens if we use the current approach, uniform number of bottles to everybody. This is what happens with if we give bottles to the highest degree. And this is what happens when we use our policy. Green is a full simulation. That was a relatively small subset, and we could do the full analysis. So how do we do that without simulation at all? The idea is to try to decrease the connectivity, because that's our only knob, right? Decrease as many edges as you can, as your resources allow. Okay, so how would we measure connectivity? Average degree makes sense, total number of edges makes sense. Maximum degree should play a role, right? Because if we have a hospital that everybody sends patients to, it's not the average degree that matters, it's the maximum that matters, right? the diameter, maybe, maybe not, modularity, for those who know what modularity, maybe, maybe not, conductance, which is what we mentioned before, some combination. It turns out that all of them, yes, of course, they play a role, but all of them are actually included carefully inside the one single number, the first eigenvalue of the adjacency matrix. So there are two sub-questions. Why is this true? And the second is what is the definition of eigenvalue, and mainly the intuition. Some of us may remember the definition, but what is the meaning? So before we see that, let's see the theorem. The Aditya Prakash and Deepak Chakrabarty and colleagues were able to prove the general G2 theorem, which says that no matter what type of virus, with immunity, like mumps, without immunity, like flu, with temporal immunity, like pertussis, whooping cough, with gestation period, with this and that and all, no matter what type of virus and no matter what type of network, there is no epidemic if the first eigenvalue is small enough. And we'll see the formula next, right? So once we have this theorem, then our heuristic for immunization is whatever you do, try to minimize the eigenvalue. Give bottles here and there, right, so that the resulting graph has small eigenvalue. No need for simulation. Still a combinatorial problem, but at least we don't need to run simulations. So here is the G2 theorem, the full citation. The Arxiv version has 10 pages of proof, very elaborate proof, but we don't need to go through the proof, right? The main point is that the one we mentioned before, for any type of virus, SIS is the flu. Susceptible, infected, susceptible, there is no immunity. SIR means recovered, which means immunity for life. SIIVV is the HIV virus. There are two types of infections, two types of vigilant states. We won't go through the details. We won't even go through the Greek letters here, right? All these are parameters of the virus. How infected, if I sneeze, how many people will get infected, what's the probability that they will get infected. Delta is what's the probability that I'll heal the next time tick. All these depend on the virus. The only thing that depends on from the graph is the first eigenvalue. And if this quantity is less than 1, then the virus, what is this virus? The flu virus has no chance. This specific flu virus has no chance. If this is less than 1, then this virus has no chance, and so on and so forth. Right? We're skipping a lot of details here, but the main point is that the eigenvalue determines what is happening with epidemic. Below a certain value, the virus will become extinct. This is what we said, no immunity, and so on. So let's spend the last few foils on describing what's the intuition behind lambda 1. The full definition is the one we said before, right? Another definition is the eigenvalues are the roots of the characteristic polynomial, so this gives no intuition at all, even if we do remember what's the characteristic polynomial. What is actually the intuition behind the eigenvalue is that it is roughly the average degree, not exactly the average degree. It is exactly average degree if everybody has the same degree and things are random, then this is average degree. Otherwise, it slightly differs from the average degree, but in the correct way. So let's see some examples. This is a chain. This is the worst for the virus, right? This is barely connected. If the virus is not lacking 2 chances, right, it will become extinct. This is a star, same number of nodes, same number of edges, let's say 1,000 nodes. But this is better for the virus, right? If the virus manages to infect the kindergarten, then all the kids will be sick and all the parents will be sick throughout the whole winter as it happens. And this is the best case for the virus. Everybody is connected to everybody else, so even a very weak virus should have good chances. Let's see what the eigenvalue says, right? As we said, here this is almost a loop. Everybody has degree 2, so the eigenvalue is almost 2 here, right? So, okay, that makes sense. What is the eigenvalue here? We don't have to think. This is a full clique. Everybody has the same degree, n-1, so the eigenvalue is n-1. So not surprising, the full clique is better, higher eigenvalue, better for the virus than the chain. Okay, good. What happens about the star? Believe me, the eigenvalue for the star is the square root of n, where n is the number of satellites, right? And this means that the star is better for the virus than the chain, right? Why? Because we said this is the kindergarten situation. If we infect the central node, then we have good chances, right? So this is exactly the point. These are the numerical values, right? And this is exactly the point, that the eigenvalue is more or less the average degree, but when the average degree is when everybody has the same degree, then that's it. When everybody has different degrees or power law degrees, then the eigenvalue is the average degree done right. Here are simulations. This is epochs of simulation. This is number of infected people in an otherwise realistic, very realistic network. This is tries to mimic the city of Portland, Oregon. 31 million links, 6 million nodes. Who infects whom? This is the SIR model, like mumps, right? The lifetime immunity. So if we are above the threshold, then the threshold of the G2 theorem, then we see a spike, a lot of people get infected, and then of course everybody gets healed, and that's it. Nobody gets infected anymore. If we're below threshold, a few people get infected, and after 10 time ticks, this is it. The virus dies out, right? This is the takeoff plot, which says if we play with the strength of the virus, if we make beta is the attack probability of the virus, if we change beta so that we are below below threshold, then very few people get infected. Footprint is how many people are infected at the end of the experiment, right? And we see that the plot takes off exactly at the value of 1, where the G2 theorem expects. The same is for SIRS, pertussis, whooping cough, which means temporary immunity. We have more or less the same situation. Above threshold, a lot of people remain infected now because they can get reinfected. Below threshold, the virus becomes extinct. The takeoff plot is exactly at position 1 where we expect it, right? So the conclusion for immunization is that for almost any immunization setting, what we want to do, we want to allocate our resources in a way to minimize the first eigenvalue, regardless of what the virus is doing. And conversely, if we are the virus, we have a new product and we want to have viral propagation of the product, then we want the reverse. We want to allocate advertising resources so that we maximize the connectivity, the eigenvalue. Let's skip that part. We are running out of time now. So the conclusions, we are thankful to all the sponsors mentioned here. This is the Pegasus software system, which is designed to analyze large graphs on Hadoop, and these are the main implementers behind it. And these are the people who are participating, who lent foils for this presentation. I would like to thank Nagiza for sending us Neil Shah for participating in this project. So there are and here are the conclusions. Big data can help us find patterns that would be invisible otherwise, right? The adult advertisers here would hide very nicely. They have only 10,000 degrees. They wouldn't show up unless we do careful analysis with state-of-the-art software, Hadoop. You may recognize the logo for Hadoop, state-of-the-art hardware. Back then it was a supercomputer, and careful matrix algebra, right? The sum of cube of eigenvalues is the number of triangles. The second conclusion is that self-similarity is a powerful tool to help us explain power laws, to help us expect power laws, or generate synthetic data that have power laws. We should be aware of the Gaussian trap, like the Friends of Friends, which will flood the whole data center just for the very first person. We shouldn't be expecting good cuts, despite the plethora of excellent graph partitioning algorithms, and the ARMAT graph generator is very realistic and passes 5 checkpoints. The third is that if we want immunization, decreasing the singular the eigenvalue is the theoretically correct thing to do. And here are the reminders. With random assignment of resources, we get a lot of infected hospitals. With careful distribution, we get fewer. This is a book which should be available for free in every library, in a lot of libraries. The big take-home message is that cross-disciplinarity pays off. All these projects that we mentioned all benefited from at least 2 or 3 disciplines each. The anomaly detection from hardware, from software, from matrix algebra. The graph generator from matrix algebra again, Kronecker graphs. From fractals, Mandelbrot and self-similarity. From dynamical systems, this is the Lorentz curve. If you are familiar with the butterfly effect, this is it. This is the first who started it. Immunization, it includes dynamical systems, medical doctors, and CDC, Center for Disease Control, and so on. And this is the end of the presentation. Yes.
So,
okay.
So we talked about the communities in the sense, if we define communities like in the sense that they have large number of edges within them but few outside, we know we cannot find good communities, right? But do you think there might be any other way of reasonably defining communities where we can find good communities?
Very good question. So the question is, if we define communities as a lot of connections within and few connections outside, we might not find such communities. Actually, this, and the question is there a better definition of communities? I don't know if there's a better definition, but I should clarify that for real graphs, it turns out that for small groups, there are very good communities. I didn't have time to illustrate that. But even for the patent graph, there is a group of 80 patents that point to 20 patents, all of them. So there's a bipartite core. For patents, it's probably not suspicious because maybe there were patents from the same company citing the 20 fundamental patents of that area, right, or whatever it was, right? But for other settings, this is a telltale sign for fraud, right? If you have 80 uncorrelated people pointing to the same, giving thumbs up to the same 20 uncorrelated products, probably these 80 people were paid. They have a company and they just follow whoever pays them, right? So we have to be careful. And for smaller graphs, once we start cutting the big graph, the Google graph or whatever, into smaller pieces, then we have reasonably good communities. So, yeah, it doesn't answer completely your question, but I don't think anybody knows. Yes, you were next.
Two questions. One is, it seems to me the eigenvalue analysis also suggests a way of self-organizing quarantines. So that you tell everybody, talk with only one neighbor or pass food along through only one neighbor, and then find somebody else if that person dies or becomes incapacitated. Because you're there, you're just trying to organize rather than cutting off a whole group when nobody talks to them.
That's right. So let me repeat the question for recording purposes. So the eigenvalue observation, the eigenvalue theorem, could also dictate how people could do self-organized quarantines, right? And that's absolutely right. So far, all the models assume that if somebody is sick, this person will continue shaking hands and continue sneezing and all that. This is not what is happening. If we're sick, we stay home. Our friends avoid us for good reason, right? So yes, there is and actually, as you correctly observe, all these actions decrease the eigenvalue, right? We start not talking to sneezing people, right? Which drops the eigenvalue. Correct, yes. You had the second question, and then I give that. Yeah.
Yeah. I keep thinking about the lip, and I'm always reminded of one of my favorite theorems. It's Erdős and I think Spencer about the connectivity of random graphs, where you have this probability the graph is connected is 0 up until you get to n square root of n edges, and then it's half, and then it's 1. The connectivity probability is 1 after for more edges. And I'm just wondering whether whether for 0 that's giving the downward slope, and then
that's a very good observation. So you're referring to the phase transition of Erdős-Renyi, right?
Yeah.
So we have 1 million fixed nodes, and we start throwing edges, right? Smith becomes friends with Johnson, and so on. And as you correctly said, when we reach a critical point, initially the graph is disconnected. When we reach a critical point, the graph with high probability is connected, right? It has a giant connect component. Maybe, but here this is not the situation, right? We're not adding or deleting. We're just cutting pieces.
Okay.
But there seems to be a phase transition. So maybe if we think more, maybe there is a connection there. Yeah. Good observation. Thanks. Agiza.
So from Spectral's theory, it looks like there's such an importance of the first eigenvalue. But at the same time, the first eigenvalue and the average degree of the graph are similar. So whether the same conclusions will hold if you replace the whole first eigenvalue computation just by the average degree?
Right. So the question is, since the first eigenvalue is so closely related to the average degree, why not take the average degree and that's it? this would be correct for graphs that have a Gaussian distribution of edges. For graphs, let me see, let me get the correct one. Right. For graphs that have very skewed distribution, like this one, this guy is super connected, 1,000 friends, and this guy has one friend, right? For this, the average degree is 2, and it's a disaster, right? And my guess is that for most of the graphs, we'll have power law degree distribution, or log normal, or very skewed, in which case the average might be completely misleading. So, but you're right. If we have reasons to believe that the distribution of degrees is Gaussian, then yeah, average degree is it. Good point.
One more question.
One more question.
Yes. Have you considered using other types of measures? You talked about the FOF, the friends of friends thing, which, of course, is not captured by the the degree distribution directly.
Correct.
So have you considered using other measures such as like the clustering coefficients and things of that nature?
Consider other measures to achieve what? For what purpose?
To actually better reflect your measures of, for instance, in your epidemiology, the type of behavior and things like that.
That's a very good point. So yes, the clustering coefficient eventually is the number of triangles averaged over a power law. So I think the clustering coefficient should not be used if we know it's a power law. But what you say is correct. And the lambda, the average, the eigenvalue, actually captures the number. The sum of cube of eigenvalues is the number of triangles, which is related to the clustering coefficient. A lot of the number of paths also depends on the first eigenvalue. If the first eigenvalue is high, there are a lot of paths from everywhere to everywhere. So it correctly captures the connectivity of the graph, and there is the 10-page proof that says this is it, right? So yes, there are a lot of other measures, but this is the result of the theorem. So yeah, I think this answers the question. So I owe an answer somewhere there, but we are running out of time, right? Okay, so we can discuss the question. There was some question. We'll take it offline. Yeah.
Thank you so much.
Thank you.